Okay, in this section we're going to talk about angles and the radian and degree measurement of angles. We're going to be on the unit circle here. Everything's on the unit circle for a while. Later on we'll talk about what happens if you're not on the unit circle. If you're on the unit circle and you have an arc length of, say, t units, suppose this is t, then we define the angle measurement of this central angle to be t radians. So the radian measure of an angle is numerically equivalent to the length of the arc on the unit circle. That's how it works. Okay, so let's locate these angles. Remember, the angles can be located in terms of thinking about the arc length on the unit circle. For example, where would the angle pi over 6 be? Well, if you march around the unit circle pi over 6 units, then this angle right here would be pi over 6. See? That's how it works. Where would pi over 3 be? Well, you start at 1, 0, and since it's a positive angle, you march around pi over 3 units on the unit circle, so that arc length is pi over 3. Therefore, this angle in here is pi over 3. Okay, let's keep going. Let's see. Suppose you want to know where the angle 3 pi over 4 would be. So if you're on the unit circle and you go over 3 pi over 4, that puts you over here, doesn't it? So this angle right here would be 3 pi over 4 radians. Let's see, 4 pi over 3? Let's see, 4 pi over 3 is down here, isn't it? So if you march around this distance 4 pi over 3, this angle right here would be 4 pi over 3 radians. What about a negative angle? How about negative 5 pi over 6? That means you're going clockwise, right? So 5 pi over 6 puts you right here, doesn't it? So this angle right here, in the clockwise sense, this would be negative 5 pi over 6 radians, okay? Let's do one more. How about 7 pi over 2? Well, let's see. 7 pi over 2, let's see. 7 pi over 2 is equal to 6 pi over 2 plus pi over 2, which equals 3 pi plus pi over 2. So we're going to go 3 pi, let's say an angle of 3 pi. This would be 2 pi, wouldn't it? This would be an angle of 3 pi. So you go additional pi over 2, so you get right there. That's the angle, 7 pi over 2 radians. So keep going with radians for a minute. So if you go a quarter of the way around on the unit circle, this angle here would be pi over 2, right? This is the angle where you end up. If you go halfway around the unit circle, the arc length of pi, this angle in here would be pi, the central angle. And if you go 3/4 of the way around, that would be 3 pi over 2. Then the central angle would be 3 pi over 2 radians. All the way around would be 2 pi radians, wouldn't it? Whereas with degrees, now there's 360 degrees in one revolution. So if you go a quarter of the way around, that would be 90 degrees. Halfway around would be 180 degrees. And 3/4 the way around would be 270 degrees. All the way around is 360 degrees. Okay, so it's important to be able to convert between radians and degrees. We're going to use this one right here. Halfway around is halfway around. That's the unit conversion we're going to use. So this is how you would do it. We want to convert these to degrees. Now again, the question is that the angle pi over 3 radians, or is that the distance pi over 3 units on the unit circle? The answer is they're numerically equivalent, so it doesn't make any difference. You can think of them as being the same. But how would you convert pi over 3 radians? We're going to use this ratio between radians and degrees, and we're going to use what's called dimensional analysis. We're going to do that quite a bit here, where you're basically converting units. You multiply by 1. Remember, pi radians on the bottom, because you want to cancel the radians, and you get 180 degrees. That's the relationship. So anyway, when you do that, you cancel the radians, and you cancel the pi's, you end up with 60 degrees, right? Pi over 5 radians, let's see, that would be pi over 5 radians. You want to cancel the radians again, so you do the same thing. You'd multiply, you want radians on the bottom, so pi radians is 180 degrees. And then let's see, you could cancel the pi's and the radians. You get 180 degrees by 5. I think that's 36. You better check me on that one. 1 radian, that's interesting. Is that the number 1? Or is that the angle that has 1 radian? And the answer is, you can think of them as being the same. They're numerically equivalent. So if you think of it as 1 radian, we want the radians on the bottom. Pi radians is 180 degrees. In this case, you're going to, all you can cancel, I believe, is the radians. You end up with 180 divided by pi degrees, which is about, it's roughly, if you use your calculator, you get 57 degrees. That actually says a lot if you think about it. Think of it like this, folks. Remember, all the way around the circle is 2 pi radians, and that's about 6.28 radians. We just showed that a radian is about 57 degrees. So think of it like this. There's 1 radian, there's 2 radians, there's 3 radians, there's 4 radians, there's 5 radians, and there's 6 radians. So it's a good chunk of the unit circle. Each radian is a good chunk. It's about 57 degrees. Okay, let's see what we got here. Oh, one last thing. Let's go the other way. Let's convert from degrees to radians. Same idea, pretty much. Let's see. 30 degrees. We're going to multiply by 1. So we're going to multiply we're going to want degrees in the bottom. 180 degrees is pi radians, right? So what you do here, when you cancel the degrees, you get pi over 6, right? Because the 30 over 180 is 1/6. Let's do one more. 15 degrees. This turned out to be very important. We're going to talk about this in the next slide here. 15 degrees turns out to be something that's going to be helpful when we locate these angles in degree measurement. We want 180 degrees on the bottom. We want pi radians on the top. The degrees cancel, right? And so you get pi. Let's see, 15 goes into 180. I think you get 12 times. Pi over 12 is what you get, radians. So keep that straight. We're going to come back to that in just a minute. Okay, before we go on any further, I just want you to sit and enjoy this beautiful picture here. Isn't it wonderful? It shows all the special angles in the first quadrant. Notice how it uses red, all the angles that have reference angle 30 degrees, blue for all the angles that have reference angle 45 degrees, and green for all the angles that have reference angle 60 degrees. You don't really have to memorize this chart, of course. I don't want you to. I want you to focus on those 3 angles, and then we're going to use those 3 angles as our reference angles to locate the other ones, right? Okay, so here we go. Let's just try some. First of all, let's recall this is 90 degrees up on top. This is 180. This is 270 degrees, and this is 360 degrees, okay? Furthermore, we were just talking about 15 degrees. We were talking about this earlier. Each of these notches before was pi over 12, right? Well, pi over 12 is 15 degrees, so what does that mean? That means every time you go 1 notch, you've gone 15 degrees more, okay? So think like that. So those will help you locate the points. I should say the angles. For example, where is 210 degrees? Well, it's 30 degrees past 180, so isn't it right there? This is your angle. Your angle goes from here to here, technically. So you're in the third quadrant. Your reference angle would be your 30 degrees, right? It'd be negative radical 3 over 2, negative 1/2. Okay, let's see, negative 225. That means we're going clockwise, negative 225. I believe we end up right here, right? Negative 225 is right here. Our reference angle is going to be pi over 4, or 45 degrees. So we're in the second quadrant, so x is negative, y is positive. Negative radical 2 over 2, positive radical 2 over 2. Okay, let's see. We're in the this next one, 330. We're going clockwise. We're 30 degrees short of 360, so we're 2 notches short of 360. We're going all the way around to here. So we're in the fourth quadrant. X is positive, y is negative. Our reference angle is still going to be that 30-degree angle. Radical 3 over 2, negative 1/2, right? A last one, 420 degrees. Well, let's think about that for a second. 420 degrees is equal to 360 plus 60 So here we go, 360, that's all the way around, and you go another 60. So we end up right here, don't we? This is our referencing point. So we'd get 1/2 radical 3/2. That's it. Okay, let's address the question now. How do you find the radian measure if you're not on a unit circle? Let's suppose you're on a circle of radius r. We're going to assume theta is measured in radians. This is the thing to really focus on, what it says right here. The arc length on any circle of radius r is a fraction of the entire circumference. It depends on theta. If theta were 2 pi, then wouldn't it be the entire circumference? But let's say theta was pi, then the arc length would be half the circumference, wouldn't it? And so on. That's all this says. So the circumference is 2 pi r. And then the 2 pi's cancel. So we just derived the formula that relates the arc length to the central angle to the radius. It says this: if you have an arc on a circle of radius r, this would be the arc length s. This would be the radius r. This would be theta. It says that the arc length theta, I should say that the angle theta, is the ratio of s to r. It's you have to divide the arc length by r. Okay? It's a little different. Now, of course, you notice that theta in radians is s over r. What if r is 1? If r is 1, then that says theta equals s, and that's exactly what we were talking about with the unit circle, right? Anyway, so we have a couple of problems here. For example, let's suppose you have an arc length. It says, find the arc length of a circle with radius 4 centimeters, whose central angle is 30 degrees. Well, the catch on this is you always have to use radian measure. So you'd have to convert 30 degrees, otherwise it's not valid. 30 degrees equals pi over 6. So you want to find the arc length. S equals r theta, which would equal 4 centimeters times pi over 6, which would equal, what is that, pi over 3? 2 pi over 3 centimeters. That's your answer. That's the length of the arc length there. Let's do one more. Find the radian measure of a central angle theta on a circle whose radius is 8 centimeters and whose arc length is 10. So we're not on the unit circle, we're on a circle of radius 8. So the formula says that theta equals s over r, so it'd be 10 centimeters divided by 8 centimeters, which I think is 1.25. Now notice, the centimeters cancel, so what does that say? That says that technically, radians do not have any units. Okay? It's okay to write RAD for radian, just to keep it straight, but technically the radian does not have any units at all. Okay, similar formula when you want to find the area of a sector of a circle. A sector is just a piece of a circle. It would look, let's see, here's an example of a sector, like from here to here is a sector. And this central angle is theta. The bigger the theta, the bigger the area of the sector, right? And that's really all this says. It says that the area of a sector is some fraction of the whole area of the circle. If theta were, example, 2 pi, then the area of the sector would be the total area of the circle. But area of a circle is pi r squared, so the pi's cancel. So this is where you get the formula. The area of a sector is equal to 1/2 r squared theta. So in this particular example here, you have, let's find the area of a sector of a circle whose central angle is 40 degrees and whose radius is 4 centimeters. Now I mentioned, for these formulas only work when you're in radians, so teachers love to give you the angle in degrees. You have to first convert to radians. That's not too hard. 40 degrees equals 2 pi over 9 radians. So then when you plug that into your area for the sector, you get 1/2 r squared, so 1/2 times 4 squared times 2 pi over 9, you end up with, the 2's cancel, you get 16 pi over 9 square centimeters. That's it. Alright, we'll see you next time. Bye-bye.